Hi everyone, welcome back to Banach Spaces webinar. Today we are very excited to have Tommaso Russo. He is in Czech Republic, Czech Academy of Sciences and Czech Technical University. And he's speaking on Asplund Banach spaces with norming Markuševič basis. Tommaso?
So thank you very much. So, well, first of all, thank you for having this idea to start a webinar when it was clear that for some time we would not have time to in-person conferences. And well, thank you as well for inviting me to give this talk here. It's a great honor for me to be here. And what I will present here is the output of a preprint, which is on the archive since more or less 1 month, I would say. And here in it's a joint paper with Petr Hájek, Jacopo Somaglia, and Stevo Markuševič. And what I will do is, well, obviously start with a brief introduction to the subject, very, very broadly speaking, then entering into an introduction to what is the problem that we were interested in, and then discussing main results and sketching also some of the ideas of the techniques that we have. So half of those more or less. So, well, I should probably apologize with some of the experts in Banach space theory, because they will find the broad introduction way too broad and elementary. But on the other hand, well, when preparing the slides, I was not so sure exactly which kind of approach try to give. So it's going to be hopefully understandable for most of us. So let's hope that this screen is visible to everybody clearly. So the main definition that they definitely need to start the topic with is the notion of a Markuševič basis, which I will mostly shorten by M basis. Markuševič basis is, as probably everybody knows, is just a system U alpha phi alpha, where U alpha are vectors in a Banach space and phi alpha are functionals on the Banach space, such that they are orthogonal, namely the evaluation of phi beta on U alpha is the Dirac delta. The vectors U alpha are linearly dense in the Banach space, and the functionals, the linear span of the functional is weak star dense in the dual, which can be restated like the functionals separate points and I mean, this is with the weak star density, and the other one is, I mean, if every functional is zero on a vector, the vector is zero and vice versa. If a vector is zero, is the kernel of a functional, the vector is zero. So once we have a Markuševič basis, there are two natural notion of coordinates for vectors and for functionals. So if you pick any vector x in the space, the coordinates of the vector are merely the evaluation of the string of functionals on the vectors, and analogously, the coordinates of the functionals are just the evaluation of these single functionals on all the vectors of the basis. And of course, what the main idea of a Markuševič basis is that it's maybe the most general way to think of a Banach space as a space of generalized sequences, because now we can speak of, now these are indeed real or complex numbers. So it's an object that we can compute with, and we can explicit object to make computations on and making estimates and whatever. So it's a way more concrete object than just having a vector in some Banach space without having any more information. But there is a difference between coordinates of vectors and functionals, in the sense that coordinates of vectors are countably many of them are non-zero, only countably many of them can be non-zero, and if the functionals are normalized, this element is in C0 of gamma, while the coordinates of functionals can be all of them different from zero in general. So some classical things which we all know is that every separable Banach space admits a Markuševič basis. This is Markuševič's result. And then with the start of the study of non-separable Banach spaces and of WCG Banach spaces, it was shown by Amir and Lindenstrauss that also weakly compactly generated Banach spaces do admit Markuševič basis. This is a fairly easy consequence of the fact that they have a projectional resolution of identity. And while here I also recorded that a Banach space is weakly compactly generated if there exists a weakly compact set in the space that is linearly dense. And on the other hand, maybe the simplest, on the other hand of the spectrum, the simplest example of a Banach space which has no Markuševič basis is L infinity. So of course we need something which is non-separable, and this probably the simplest non-separable space you might think of is L infinity. And there is this result by Bill Johnson that L infinity indeed has no Markuševič basis. So as I commented before, the functionals, the coordinates of the functional behave in a weaker way than the coordinates of the vectors. This is reflected by the fact that the linear span of the vectors is dense in norm, while the linear span of the functionals is merely weak star dense. So it's, in a sense, on the functionals we demand a bit less in this sense. So it is tempting to ask if the finitely supported functionals, this linear span of the functionals, is not just weak star dense, but might end up having better properties. So if it exhausts the dual in some stronger senses. And of course, there is a natural strongest definition, which is in perfect accordance to the one for the Schauder basis, which is the notion of a shrinking basis. So a Markuševič basis is shrinking merely when the linear span is dense in norm. So not in the weak star topology, but in the norm topology. And this one is indeed a very strong assumption, and I will turn later on how strong this indeed is. There is something in between, which is the normingness notion, of course. Weak star density, normingness, and norm density are, of course, linearly increasing by strength. So in general, a subspace is said to be norming if this formula here is valid, namely, if you want to norm a vector of the Banach space, you can reduce yourself to using functionals from this subspace. So the supremum of the evaluation of phi on X, where phi is in this subspace and is of norm at most 1, this is at least a multiple of the norm. And of course, the inspiration for this notion is the Hahn-Banach theorem, because by the Hahn-Banach theorem, if you pick as Z all the dual space, what you get here, this right-hand side, is exactly the norm of X. So the dual is always a one-norming subspace. And having this notion of normingness, of course, we can define a Markuševič basis to be norming if this finitely supported functionals here, this linear span, is a norming subspace. So a basis is norming if the span of phi alpha is a norming subspace, namely if this formula here holds. And as before, well, we might ask, what do we know about norming basis? The first thing is Markuševič's proof does give a norming basis. Or maybe the proof doesn't, but it can be easily adjusted to give a one norming Markuševič basis. In the reflexive range, well, it's clear that every Markuševič basis is shrinking merely because weak star density in the reflexive spaces, weak star topologies is the same as weak topology, so any basis is necessarily shrinking. So reflexive spaces do have Markuševič basis because of Amir-Lindenstrauss, and so they do have shrinking basis. And one result that we noted in this research, which is fairly simple after all, but still decently general, so I found it interesting to have it, is the fact that C of K spaces where K is an adequate compact do have a one-norming Markuševič basis. This will not really play any role for the folk later, so I just commented with here because I think it's a decently general result, but it's not going to be extremely important for the main part of the talk. So the natural question that came up when Markuševič bases were studied was how strong this notion of norming basis is. And this, of course, came along with knowing which spaces do have a norming basis and which spaces do not have a norming basis. And in this direction, of course, L infinity has no norming basis because it has no M basis at all. But a more interesting result is the space of continuous functions over the unit interval zero, not the unit interval, the long interval 0, omega 1, which was shown not to have any norming basis by Alexander and Plichko. This paper has a strange maybe story, I would say, because it was published in 2006, but it appeared online at least 10 years before. So if you check the article, you will see that there were 2 referring procedures. So the result is much older than the paper in this sense. And this fact is rather important also because this space is quite close to having norming basis in a sense, because it does have decent systems of coordinates. It does have a monotone long Schauder basis, and it also has accountably one norming Markuševič basis. So no norming basis, but it does have a countably norming basis, which is a weaker version. And I will not really define countably norming basis. I will not really need it, but I'm just mentioning that this is in a sense the prototypical example of a space failing norming basis, but being quite close to it, to having it. So if you want to know how strong the notion is, well, this is a good example to keep in mind, of course. And well, in the separable case, Schauder bases are norming, and long unconditional bases are norming as well. So in a sense, the separable Schauder theory is stronger than the norming basis. But on the other hand, there is an extremely elementary observation, namely if you have a lambda norming M basis, let's say of length omega 1, then you can pass to an uncountable subset lambda of this omega 1, such that if you extract just these vectors when the index ranges in lambda, these vectors form a long basic sequence. So if you have a lambda norming basis up to passing to an uncountable subset, what you have is actually a long basic sequence. So in a sense, norming bases imply long basic sequences, so they are stronger than long basic sequences in this sense. And I would very, very briefly comment on the proof, because the proof is entirely obvious. It's just Mazur lemma. So the unique thing to note is that if you pick any separable subspace of X, by normingness, you can norm simultaneously all the vectors of Y using a countable set. This is because you can norm any element in Y with a countable set and then pick a then subset and you're done. So there is a countable set S such that the span of countably many of the functionals is already norming. And now you just put this observation in Mazur's technique. Mazur's technique requires to norm some initial piece and then pick vectors in the kernel of the norming functionals. So here we just do this thing, norming with these vectors, these finitely supported vectors. So the proof is really, I would say, essentially is Mazur result. However, I have to admit, I'm sure that somebody observed this before, used and probably wrote in some papers before, but I'm not aware of a reference for this. So if somebody of you has seen this before and is so kind to point it out to us where we can look for it, just for giving a reference, because it's good to write it somewhere. So well, here I wrote this fact that norming bases are in a sense stronger than long basic sequences, and stronger really means strictly stronger because of this example here of C, the continuous function of 0 omega 1. There is a long basic sequence, but there is no norming basis. So this is a strictly stronger notion. And of course, concerning this direction of results, I have to mention perhaps the most famous open problem concerning norming basis, which has been asked by John and Zizler in 1974, namely if every WCG Banach space admits a norming Markuševič basis. This, of course, is a natural question concerning the strength of the concept of norming Markuševič basis. And I mentioned that this, as an open problem, this has been open for almost 50 years, but it was solved by Hájek in the negative 1 year ago by constructing a C of K space, which is weakly compactly generated and which does not have any norming Markuševič basis. And as a matter of fact, the compact K, which is constructed, is not just Haberline, is also uniformly Haberline, which means that the C of K space is additionally Hilbert generated. So it's not just weakly compactly generated, but it's also Hilbert generated. So this is definitely a very strong answer to how strong norming Markuševič basis might be. So now I would enter a bit more, which, of course, what we will discuss in this talk is going to be norming Markuševič basis, but now I will discuss more in detail what about them. And as I maybe hinted at a bit before, Markuševič bases have been used by many authors in different directions, frequently in order to characterize some classes of Banach spaces. For example, it is known how to characterize weakly compactly generated by means of weakly compact Markuševič basis. Shrinking Markuševič basis characterize another class of Banach spaces, as I commented before, and as I will mention in this very slide. Countably norming bases are very tightly connected with WLD Banach spaces and Plichko spaces, so it's Corson and Valdivia compacta. And of course, these are several notions which were introduced after the notion of normingness. So it was of course natural to wonder what class of Banach spaces can be characterized by having a norming basis. And John and Zizler's problem from the previous slide was a question in this direction, trying to understand how to characterize spaces with a norming basis. And in order to recall the shrinking criterion, the shrinking characterization, not criterion, I would recall the other notion appearing in the title, which is the notional Asplund space. Banach space is Asplund. Well, it can be defined in lots of ways. It was probably originated probably by defining with a definition involving the differentiability for convex functions, but it's probably no more customary and definitely shorter to define it in this way. A Banach space is Asplund if separable subspaces have separable dual, which is the shortest possible definition, one line, perfect for slides. And the thing we will need to know is that in the C of K category, C of K is Asplund exactly when K is a scattered compactum. And this we will use. So, I mean, if you want to keep in mind the objects we will consider, I won't need more than Asplund spaces, WCG spaces, and norming Markuševič bases. So definitions are more or less over, so which is maybe good to know. And now I can state this important result, this very elegant characterization of spaces admitting a shrinking basis, because a Banach space admits a shrinking Markuševič basis precisely when it is simultaneously weakly compactly generated and Asplund. So shrinking basis is exactly equivalent to both WCG and Asplund simultaneously, and it's also equivalent to being WLD and Asplund, or again being WLD and the dual admitting a dual locally uniformly rotor norm. So this result has been known since some time. It follows from the contribution of several authors. I listed some here. I probably didn't manage to list all of them. I'm not sure. I mean, I am aware of other papers which I didn't list. There is a way to prove the result using only one result from a paper by Marian Fabian and one result from a paper by Orihuela and Valdivia. But these two papers were building on different previous papers from John Zizler, Trojansky, and other people. So I listed some earlier contributions as well. So as you see, this is a very elegant characterization of spaces with a shrinking Markuševič basis. And since norming is weaker than shrinking, one might wonder if this result might give an indication of what a norming basis might be around to characterize. So before thinking at anything sophisticated, let's have a look at an obvious example. An obvious example might be the space L1 of gamma, little L1 of gamma, where the canonical basis is one norming. However, this space is not exactly well behaved. It is not an Asplund space, and it's not a WCG space if gamma is uncountable. So, for example, you cannot hope that norming basis would imply the space to be norming or to be Asplund because of L1 omega 1, which has a norming basis but is neither WCG nor Asplund. And likewise, the space L1 shows that even if you assume one of the conditions, you're not gonna get the other one. So if you have a norming basis on a WCG space, you are never gonna get Asplundness in general, right? Well, every separable Banach space with non-separable dual in reality, not just L1. On the other hand, well, maybe if you swap the roles here, it was not obvious at the time to want to find something which would be Asplund with a norming basis which is not WCG. And this was actually came as an open problem asked by Gilles Godefroy for the first, apparently from, it's by now attributed to him. I don't know if somebody before Gilles came out with this problem, but it's by now it can be traced back at least to Gilles. And the question is if you can, if you pick an Asplund Banach space which has a norming basis, if this space has to be necessarily WCG. So, I mean, I would spend some bit of time discussing this question for some reasons. Well, essentially because this is the main problem we'll be interested in the talk. So the first thing is, John Zizler question was like, WCG implies norming or not. Here, in a sense, it's kind of a converse. So norming implies WCG under some restriction, under the restriction of Asplundness. But somehow, in this regard, we can consider this problem as a converse to John and Zizler question. And moreover, this is tightly connected to the theorem above because of this comment I made before, also because here you see that WCG plus Asplund implies shrinking, but at the time it was conceivable that norming basis was a more general notion than WCG. So it was conceivable that one could generalize here WCG with norming basis. Now we know that this is not a more general assumption, but still it might be reasonable to wonder if here one might put norming. After all, if you have WCG and Asplund, you even have a shrinking basis. So at some point you will build a basis. So assuming already that you have some basis is not a crazy assumption. So this question came out, I mean, I've been emailing Gilles a few times about the history of the problem. So, well, I also take this opportunity to thank him again for so kindly replying to my emails. And what he told me is that he came out with this problem at the time when they were writing their joint book with David and Zizler, smoothness and renorming, because there they have some non-separable results connecting as well with WCG and Jane Rogers selectors, which might have been useful for the problem. And so this is the main problem we will deal with in the talk. And here is what we were able to show. Our answer is a negative answer to the problem. So we were able to build an Asplund space with a one norming Markuševič basis, which is not weakly compactly generated. So shortly, very shortly, the answer here is just no. We actually do slightly more in the sense that just checking the system that we build, this system here is also normalized, both in the vectors and in the functionals. So F gamma and mu gamma have norm 1. So this is the so-called Auerbach system. And moreover, we can assume that these vectors f gamma are also a long Schauder basis, a monotone long Schauder basis. The reason for this is extremely simple. If you remember the folklore factors I mentioned before, so vectors will be a Schauder basis, Schauder basic sequence, pardon. And now the X with this closed span of these uncountably many vectors, then, well, it turns out that...
Tommaso, can you repeat the last thing? Your voice cut out.
Yeah, I saw the connection was unstable. Okay.
Yeah.
Okay,
just repeat the one you started with the folklore result.
Yeah, so now if I pick the closed span of these uncountably many vectors, this closed span can be shown to satisfy the theorem as well. So the point is, in the construction, it's not just the closed span of all vectors to be a counterexample, but also the closed span of every uncountable subset satisfies the condition as well. So in some sense, this example is hereditary. If you pick any uncountable subset and pick the closed span, this closed span also gives an example, which combining with this easy fact gives the conclusion that we can assume to have also a monotone long Schauder basis. And what we do is, as maybe somebody could have guessed already from the notation I was using, f gamma and mu gamma, what we do is we build X as a subset, as a subspace of a C of K space. So we will build a C of K space, a scattered compactum, and then X will be a subspace of this C of K. So I will discuss how to build this compact K. It will be essentially the main part of the talk. It will be discussing how to find this compact. And so our example is indeed subspace of an Asplund C of K. And this is also some non-trivial information. What we don't know, and this is why I was mentioning this, is we don't know if we can even obtain a C of K counterexample. So our example is subspace of an Asplund C of K. We don't know if there is a C of K space that is also a counterexample. This is a problem which we thought for quite a long time, and we don't see any answer yet. So yeah, now I think it's time to discuss the second theorem, which will be devoted to describing properties of this compact. And in order to do this, I need to give a small piece of notation. So if you have any set gamma, you can define in a natural way a compact topology on the power set of gamma, merely by the classical identification between a set and its characteristic function. So we can identify the power set of a set gamma with all the functions from gamma to 0, 1. So this is compact in the product topology, and you just pull the product topology back to the power set. So we obtain a product topology on the power set of gamma. And since the product topology depends on finitely many coordinates, neighborhoods of a set here will just be, if you pick a set A, a subset of gamma, a neighborhood will be given by all sets that agree with A on finitely many coordinates. So if you pick some A naught AN inside the set and some B naught BN outside the set, a neighborhood will be given by containing the AJ and not containing the BJ. So finitely many coordinates. This is, well, probably this is, could have been even skipped, I don't know. So why did I record that? Well, because this compact K that I mentioned to exist before satisfies the following properties. So we were able to build a family F rho of finite subset of omega 1. So we have lots of subsets of omega 1, finite ones, such that when we pick the closure of this collection in the pointwise topology, then this family has the following properties. So the first one is easy. We just know that we contain all the singletons. So our family contains all singletons. It also contains all initial intervals. So in my mind, I think that there are three levels in this, three level of points in this compact. There are the singletons at the very bottom level. Then there are at the very top level, all the initial intervals, 0 alpha, which are infinite sets. And then I have to say what is in the strip in between. And the main part of the theorem is that the strip in between only consists of finite sets. So infinite sets are only initial intervals. So when you take the closure here, what you add is either a finite set or an initial interval. So the structure of infinite sets here is extremely rigid. They are only initial intervals, which is the very main peculiar property of the space. And as a consequence of this, one shows that the space is scattered. So as you will see, the property 4 will follow from the third one in a not so complicated way. So I will discuss something about theorem B later. Here I will just have one slide to say, once you have the compact K row, how you continue to go to theorem A. I just mentioned how to build a orthogonal system. So you define some functions f gamma in the following way: f gamma on a set, because f gamma is a continuous function on K row, so I have to define f gamma on any set A in K row, and I just say that the function is 1 if gamma is in A and it's 0 elsewhere. And the measures mu gamma is nothing else than the Dirac measure on the singleton gamma. Recall that I said before, all the singletons are in the compact, and now the measures are merely the Diracs over the singletons. So as you see, the orthogonal system is very easy to define, and it just turns out to be the right construction. So in a sense, the magic is all in theorem B. And well, it is an orthogonal system. This is simple to check. And so where is the counterexample after all? You pick the closest span of the vectors here, pick the closest span over this f gamma, and this resulting space x row is the space that proves theorem A. So I won't say more about it, in the sense I just wanted to say that in a sense the main ideas to me are hidden in the proof of theorem B once you have theorem B. Of course, here there is something to verify, but in a sense, the most interesting part to me is hidden in theorem B. So now I will go there, and in order to go there, I need to export a tool from mathematical logic, maybe from set theory, more of set, no, definitely from set theory, not from logic. And this is the so-called the row function that have been introduced by Stevo Todorcevic in this paper here, and that have been appeared in several books, among which there is Stevo's book about works on ordinals. So a row function will be some function from omega 1 square into omega. So here, omega 1 to the square denotes the subset of omega 1 of cardinality 2. So they are function that to a subset of omega 1 of cardinality 2 associates a natural number. So of course, if I pick some element here, this is gonna be a pair of distinct ordinals, which is not ordered, but I can always order it, picking the first element to be smaller than the second. So I can identify omega 1 square with a pair of ordered ordinals where the first is smaller than the second. This is just convenient because now I can write row of alpha beta without having to put the brackets in between. And when I write so, I always mean that alpha is smaller than beta. So this is, well, this is entirely customary notation in this context. So the notation is really taken identically from Stevo's book. And as I said, well, I said just before that we will write row alpha beta, meaning that alpha is less than beta, and now I contradict myself, because in reality we will also pick boundary conditions. So on the diagonal, it will always be the case that rho is defined to be 0. This is convenient. So we also set rho to be 0 on the diagonal. And now, so far I defined the domain of the function. Now I say, what is this function gonna do? So our rho function is any of the function with the property above such that it has three properties. The first one is that if you pick some alpha and you look before alpha, so you look at all psi smaller than alpha, such that rho is at most n. So if you pick alpha, you check before, you see the points that are sent in something smaller than n, this set is finite. Of course, there are countably many psi smaller than alpha because we are in omega 1, so alpha is less than omega 1. So there are countably many psi's before alpha, and only finitely many of them give small values. And the other properties of the function rho are some forms of triangle inequalities. So if you pick alpha smaller than beta smaller than gamma, you have the ultrametric inequalities, but with specific orders. So rho of alpha gamma is bounded by the maximum between rho of alpha beta and rho of beta gamma, and likewise rho of alpha beta. So the rho between first and second is bounded by the maximum of rho alpha gamma and rho beta gamma. And this kind of resembles triangle inequalities, of course. So I will definitely happen to say that rho is at some form of distance, and in this sense, I would probably say the rho distance between alpha and gamma to mean this number here. And in this sense, if you check here, well, this is exactly a closed unit ball, not unit, a closed ball centered at alpha and of radius n. So this set again is nothing strange, it's kind of a ball. So if you pretend that this rho is a distance, it is not. But if you pretend for a second that it is, then this object is kind of a ball, and the first condition is kind of balls are finite. So everything is beautiful, but well, do they exist? Yes, they do. And there are many constructions in this Stevos book that one can pick. And in our talk, we will need a rho function that has some properties that are listed here. The first one is that outside the diagonal, rho is strictly positive. This is nothing special. You just can. This is not a real assumption. You can always obtain it without any effort, just sum one. So this is easy to get. This one is the first triangle inequality. So the first of the two inequalities from before, which I repeated just because I really need these three of them. So I just stress the one that I will need more. And then there is the last condition, which is a form of injectivity in the first variable. So if you pick gamma and you check before, rho, this should have been, so, pardon, this rho is equal to this rho. I forgot to put a bar here as well, pardon. They are the same rho. So the function rho is injective in the first variable, in the first entry, once fixed any second entry, which is extremely important, as I will mention in a second. So if we have this rho, if you fix this function rho, we can define our compact as follows. So first of all, let me remind this set, Fn alpha, which is the set that I was saying before, it's a finite set. So it's kind of the rho ball centered at alpha and of radius n. The collection of finite set is exactly this F rho. So F rho is the collection of all this Fn alpha. So the finite sets are exactly this Fn alpha, and K rho is the closure. So the definition of K rho depends essentially on fixing this function rho with these properties, and now we'll mention some easy properties that we derive immediately from this definition. The first thing is that F0 of alpha is a singleton alpha, just because rho is strictly positive outside the diagonal. So the ball of radius 0 is just a singleton. The second condition is that Fn alpha is a finite set. We said it already, but now it has cardinality at most n plus 1. It doesn't really matter that this is n plus 1. What matters is that the cardinality is bounded uniformly in alpha. So for every alpha, the cardinality of Fn alpha is at most n plus 1. So this is the important thing. the important thing is that the cardinality of Fn alpha is bounded uniformly in alpha. So there is a constant which depends on n, but not on alpha. And this is consequence of this injectivity here. Just because, well, this set is where rho psi alpha is bounded by n, but for every j smaller than n, there is at most one psi for which rho psi alpha is j by the injectivity here. So this is clear as well. And then if you now again fix alpha and let n grow, this Fn alpha converges to the interval 0 alpha. So now I defined this compact K, and now I can restate the theorem. So the statement here is merely that this K rho has the properties to satisfy theorem B. And now I will mention how to prove this. The first property is obvious because the singletons are in K rho, because the singletons are F0 alpha, as I mentioned already in the slide before. The second one is easy as well. I have to show that every initial interval is in K rho. But as I said, if you pick some Fn alpha and you let n tend to infinity, what you converge to is the closed interval 0 alpha. So here, if I want to obtain any open interval, well, closed intervals in the ordinal one are dense in the open one, so it's not going to be a surprise that I can find also the open ones. So if alpha is a successor ordinal, 0 alpha is just the closed interval 0 alpha prime, where alpha prime is the ordinal before. And now this is in K rho because it's the limit of Fn alpha prime. And at limit ordinals, I just observe that 0 beta plus 1, where beta is less than alpha, converges to 0 alpha. So this is extremely simple, is encoded in this property here already. And now, as I said it before, 4 is a consequence of 3, and 3 is the main part. So I will briefly say how to show 4 from 3. So I have to show that it is a scattered compacton. Well, pick any closed subset. There are two cases. Either every element in this closed set is finite. No, not finite, sorry. Either every element D in this set D is an initial interval or not. If every element in D is an initial interval, it means that D is actually contained in this part of initial intervals, which is homomorphic to 0 omega 1, and 0 omega 1 is scattered. So in the first case, D has an isolated point because it's a subset of 0 omega 1. So I can assume that I am in the other case. So I can assume that there is some element D naught in D, which is not an initial interval. What does it mean? Well, it means that it contains some beta and it does not contain something before. So there is alpha less than beta such that alpha is not in the set and beta is in the set. And now we just extend this D naught. We pick a maximal element, M, with the following properties. It contains D naught, but it avoids alpha. So I pick a maximal element with these properties. I keep on extending and always avoiding alpha. So since I always avoid alpha, I cannot find an initial interval because there is a hole at some point at point alpha, which means by the property, the third property, that this set M must be finite. But now a maximal set, which is finite, is an isolated point. Why? Well, because if you now pick the following neighborhood, all the elements in D which contain M and do not contain alpha, this is a finite amount of information because M is finite. So this is only finitely many conditions. So this is an open set. However, by definition of maximality, this set reduces to M because there is any element here will be an extension of M. And I said that M was maximal. So M is isolated, which is what we wanted to see. So this shows how to get 4 out of 3. And now I have to discuss how to show 3, and let's go there. Here is a brief reminder what third condition is. Infinite sets are initial intervals. and is also the reminder of what Fn alpha is this row ball of center alpha and a radius n. And I will distinguish two cases. The first one is where the set A is exactly countable, so it's already infinite, now assume it's countable, and then I will check what happens if it's of cardinality omega 1. So I pick some element in alpha in the set A, and I pick anything before. I need to prove that the thing before is in A as well. So showing it's an interval means pick something, everything before is in the set as well. So this is what we want to. Now, since the set A is countable, by the Fauché-Horizon property, you know that if you are in this, anything which is countably supported can be approximated, in the closure can be approximated by sequences can be approximated by a sequence. So this element here is in the closure of F rho because it's a point in K rho, which is the closure of F rho. So this is in a closure, and since it's countable, it can be approximated by a sequence. So we can pick a sequence Fn k alpha k that converges to A. And now there are two cases. If these indexes here are bounded, let's say bounded by sign M, then recall that the cardinality here was bounded by the parameter n uniformly in alpha. So this would be bounded by m plus 1 in reality as well. But if these sets have uniformly bounded cardinality, their limit is a finite set, which is impossible by our assumption here. So this condition cannot happen. So now pass to a subsequence and assume that every nk is bigger than rho alpha tilde alpha. This is because this is element in omega, so you can always go above it and assume that every nk is above this number. Next, we have this convergence, and we know that alpha belongs to A. So by the pointwise convergence, we can assume that alpha belongs to these sets here up from some term on. So again, I discard some terms and assume that it belongs to every of them. What does this mean? Well, alpha belongs to this set means that alpha is bounded by alpha k, and rho, the distance, is bounded by nk. And now I have two distances, this one and this one. So rho alpha tilde alpha and rho alpha alpha k are both bounded by nk. I use a triangle inequality, and I derive that rho alpha tilde alpha k is also bounded by nk. But this does mean exactly that alpha k belongs to this ball, the ball fnk alpha k, which shows what I wanted, because now alpha tilde belongs to this set. This set converge to A. Passing to the pointwise limit, I get that alpha tilde belongs to A as well, which is exactly our goal here. So the case of countable sets is done, and now I will show that the uncountable case actually can be reduced to the countable one in the most natural way to avoid a problem, just reducing to the previous case. So I need to recall one notation which I essentially used already. This is the sigma product of real lines. It's a well-known object in non-separable Banach spaces, in particular in the topological part, in Valdivia compacta and so on. So the sigma product, sigma of gamma, consists of all these functions from gamma to 0, 1, which support is countable. So they are 0 on all but countably many coordinates. And I need to recall a very elegant characterization due to Deville-Godefroy and later extended by Calenda. So the Deville-Godefroy result is the famous theorem that a Valdivia compactum is Corson if and only if it does not contain the interval, the ordinal interval 0 omega 1. And Calenda extended it in the following way. So if you have K in a compact subspace of 0, 1 to the omega 1, such that the countably supported vectors are dense, and such that there is a point outside which is not countably supported. So you pick, so you assume that densely many vectors are countably supported and you pick somebody which is not, then this one is not coarson because there is something outside the sigma subspace. And then, so you can find an embedding of 0 omega 1 because of the Wilcox result. But Calendar's result is more precise because it tells us exactly how this embedding looks like. First property is the embedding phi maps every countable ordinal into the sigma subspace. So if alpha is countable, phi of alpha is in the sigma subspace. The last point, omega 1, goes exactly to this selected point outside. And then we have this monotonicity condition. The supports are increasing. So if you think that the uncountable points stay above the others, it means that this 0 omega 1 kind of goes upwards and leaves the sigma subspace only at the last point, and it ends up exactly where you want it. So in a sense, it's a pointwise version of the Wilcox result. And we shall use this Calendar's criterion. So we do have, in our case, we pick a set A, which is uncountable, and our goal is to show that this has to be an initial interval. So pick A uncountable and apply Calendar's result. Since it is uncountable, it can be approximated by, it can be seen as the last point of an embedding of 0 omega 1. So there is a function phi from 0 omega 1 to k0 such that phi of alpha is countable for the first ones because for countable ordinals, the phi of alpha is a countable set. Phi is an increasing function because of this condition on the support. And last condition is that phi of omega 1 is our set A. But now phi is continuous because it's an embedding. So this means that when approaching omega 1, these sets have to converge to the set A. So the union of the sets phi of alpha is A. But now this union is an uncountable set, and this is an increasing union. So there is no doubt that these sets are going to be infinite from some point on. But if they are infinite by the previous case, they are initial intervals. And if you pick a union of initial intervals, well, increasing union of initial intervals, the union is going to be an initial interval as well. So we proved as well that the other case, that this is an initial interval as well, which is the claim that we wanted. So this concludes the description I wanted to give of the theorem. And as you see, well, there are many ingredients. Of course, there is this heavy use of row functions. And in particular, there is this uniformity, which I was using here in a very heavy way. So it's not just some row functions, we really need this uniformity encoded here. So this is one of the, so this is the part I wanted to describe in detail because I find, well, it took us lots of time to find out that this was the right tool to use. So I wanted to let people know that these row functions can be used in this way as well. They have been used in Banach space theory many other times already. So this is not the first time they appear, but this is one other way of using them. And I will have just a couple of slides in the last couple of minutes, maybe, briefly mentioning something that we know about semi-Eberlein compactor related to our theorem B. So, well, I would start from the bottom part of the slide in reality, just decided. So here again, the sigma subspace is countably supported vectors, as I mentioned. And now here I remanded definitions of Eberlein compactor. So a compact is Eberlein if it is homomorphic to some k contained in 0, 1 to the gamma, which actually embeds in C0 of gamma. It is coarson if it can be embedded in the same way, but not being contained in C0 gamma, being contained in sigma of gamma. So these are classical definitions. And then passing from coarson to Valdivia, what you demand is not that K is contained in sigma of gamma, but just that densely many points are contained in sigma of gamma. So K intersection sigma of gamma is dense in K. Now, typically one thinks that these properties are as being linearly ordered. However, if you put them in a square, there is an obvious hole here corresponding to well, not every point is in C0 gamma, but densely many are. And this was a hole which has been filled by this notion of semi-Eberlein compactum, which was introduced recently by Wiesek, Kubisch, and Arkady Lederman in 2004. So the definition is this one, something which is homomorphic to K in 0, 1 to the gamma, such that vectors in C0 gamma are dense. And in the very same paper, Kubisch and Lederman proved that semi-Eberlein compacta cannot have p-points. And this result was used by them to show that semi-Eberlein and Corson are distinct notions. In particular, there is a Corson compactum which is not semi-Eberlein, while the converse is much easier. A semi-Eberlein compacta which is not Corson is very easy to build. You can just pick 0, 1 to the omega 1, which is semi-Eberlein and is not Corson. So it is very easy to find things that are semi-Eberlein and not Corson. The converse one is definitely harder. It depends on this result, and it also depends on the construction of by Todorcevich of Corson compactum, which is the one who is not semi-Eberlein. And I mentioned p-points, so here is the definition. A p-point is in a topological space is a point which is not isolated, but if you pick a countable set of neighborhoods and you intersect them, you still remain a neighborhood. So the set of neighborhoods is closed under countable intersections. And there is a weaker notion, the one of a weak p-point. And this, in the paper, they were wondering if semi-Eberlein compacta can admit weak p-points. What is the definition? Well, a point is a weak p-point if it's not isolated, but it is not a limit of a sequence outside an injective sequence. So you cannot reach it with a sequence from outside. And well, our compact K rho is also is a semi-Eberlein because semi-Eberlein need C0 gamma being dense, and in our case, the finitely supported vectors are dense, so these are in C0 gamma. So our compact is semi-Eberlein, and it does have a weak p-point. Which one? Well, the unique uncountable one, because it's not isolated, because its limit of it can be obtained as a closure of finite ones, of finite sets, but it cannot be reached by a sequence because the unique uncountable set, I mean, if you pick a sequence, all the other elements are countable. So a sequence of countable sets will never converge to something uncountable. So if you want to remind the statement here is, if you pick there is a unique uncountable set. So how can you approximate it with a sequence of countable sets? There is no way. So this construction in theorem B also, I mean, after we obtained the other result, we were reading this paper and we realized that we also found a solution to this problem here. So slides are over, time is over as well, and probably also a bit late. So I think I'm definitely ready for stopping. So thank you very much for your attention, and I'm done here. Thank you.
All right, thank you so much, Tommaso. That was a beautiful talk. We can take questions now if anybody has questions.
Yes, this is Gilles Godefroy talking. Thank you, Tommaso, for this very nice lecture. I had a question which might be trivial. I don't know. You will tell me immediately. If you strengthen a little bit the Asplund assumption, that is, if you assume that the Schlenk index is countable, I believe that in your space, the Schlenk index is probably omega 1. I mean, it looks very likely to me.
Yes, it is. Yeah, it is.
A space with a countable Schlenk index and norming and basis, do you think that you could possibly show it's WCG or is it just nonsense?
I don't remember exactly. I'm quite sure that at some point we were discussing, the reason why our space is not WCG is the dual ball contains 0 omega 1. This is how it goes, the proof goes. So in that case, the Schlenk index definitely is uncountable. Mm-hmm. And if the Schlenk index is countable, I believe at least in the C of K case, I'm not sure I'm sure I have the discussion with Peter already. So if I think more carefully, I will probably be able to give you a better answer. Okay. But at least in the C of K case, it should be easy to see that yes. So here it should be yes, at least in the C of K case. In the general, I'm not. I should think at it a bit more, but
okay.
No, but for sure it's a very natural point to raise, and we had it in our mind. We probably forgot writing it in the paper. So thank you very much twice for the question and for reminding me that maybe we should.
You're welcome, Tommaso. Thank you.
Okay, thank you. Any others? All right. If not, thanks again. Okay, thank you so much. Yes, I'm going to stop.